Okay. You've seen this. I don't know if you've remembered or if you've read it, but you have to be careful that when you do a test using the confidence interval, it's not always the same when you're doing it like with the p-value. Okay, so here's the requirements, right? The rationale about why we're not using the binomial, right? N times P1 and N times Q1 is greater than 5. Okay, we were using this all along. You may not have remembered it, but this is how we can substitute the normal or the t-student distribution instead of using the binomial. The binomial is a discrete distribution. The other ones are continuous. So it's a little bit easier to use. Okay, so this is if you remember that this is the deviation for a binomial distribution. Instead of S equals this. P1, that's the probability of success times the probability of failure divided by the number of data samples in the first sample. Are you with me? You are? Really? Okay. So now this is talking about the deviation, or remember when it's squared it's called variance? Anybody remember that? Okay, so now I want to know what is the deviation of the difference? So if you were to calculate your paired data, right? And you want to know, find a difference between each one, right? So you have a difference between before and after, but it's paired. It's paired with what same student before and what the student learned after, right? So, I mean, I could do it for this class. Let's say you get your final, and I say, okay, now either passing or failing, depending on whether. I mean, have you learned any statistics by the end of the class? So I would give a general statistics maybe test, and I could get a proportion of people that passed it. And if I got it where it's 50-50, that means I didn't do any help at all because you could just as well guessed. But anyhow, so here we have the variance of P1 and the variance of P hat. Do you remember what hat is? Here, by the way, P hat. What's P hat? Yeah. Remember, we think that it's P. That's the null hypothesis. Remember, P1 equals P2? But what we're using as a standby are the P hats. Do you remember that in the single case? We had a single case was just talking about 1P, but still, and there's the deviation of that. Do you notice there's no square root here? Because these are squared. This is what it is when it's a standard deviation that has a square root. Okay, so that's why here. Okay, so this is what we called a pooled, because this is introducing sample 1 and sample 2. Sample size 1, sample size 2. P2, Q2. Okay, what I'm trying to say is that when you get the difference between each individual person, yes, that now you have one column of differences. That has a distribution too. Right, because it's coming from random variables. Now this is the difference of two random variables, and you're creating one, the difference. Right? And that's how you can test, and you can make inferences about the differences, whether they're equal to 0, P1 equals P2, or they're not. It'll make more sense, I think, in a second. Let's. Okay. So we have this thing here that you've not seen before, I don't think. It's called P bar. And Q bar. That's different than the hat. Okay, so this is called a pooled deviation. See, it's the deviation of the differences between our P hats, the P1 hat and the P2 hat. What's it equal to? If it were just P1, it would be equal to this. That's what you're used to doing. This guy right here, just this guy. But because we have two samples, we have a pooled deviation. It's the deviation of the one plus the deviation of the other. Now, when we try to calculate what is, okay, so now take a look at what Q bar is like before. Remember, like a failure? That's 1 minus P bar. Now, to calculate this, P bar, do you see where it says what P bar is? This is a new thing. Instead of being P hat, we have P bar. And the reason that we have a P bar is because we're pooling the two variances together. So here's, you take x1 and x2, right? And then you divide it by n1 plus n2. So, and then you replace P1 and P2 by P bar and replace Q and Q2. So, if you look here, you see how this one has a square? So that, no square root. And this has no square root, right? So these two names are the same. But I've replaced P with P bar and Q with Q bar, right? And this is still the sample size. Okay, it's a little bit weird, but what can I say? It's just pooled. Now, that when we know the distribution of these two is approximately normal with the mean of P1 minus P2 and a standard deviation of what we saw above. Now, we're going to generate what? A test statistic. And what are we going to do with a test statistic? We're going to say if it hits in the accept region or the reject. No? Okay. Maybe I go back and show you this, how we did it with a 1. But let me finish this anyway. Oh, okay. So here's the basic. You want to use Statcrunch, whatever you want to do. Okay. So you go to proportion stats, drop down the menu and select to sample with summary. Enter the number of successes and the number of observations. And then you have to set up your hypothesis test, just like we did before. I'll show you one on the computer, on the Statcrunch. So, so they enter as 0, meaning that the difference between these two is 0. That there is no difference between one sample and the other as far as the proportions that we're comparing. Okay? And then we'll calculate the confidence interval. Do you remember the confidence interval was the God's truth plus and minus man-made p-hats plus the error term? Okay? It's going to look a lot more complicated now because we have 2. So let's take a look. Okay. There. This is the test statistic. Now, if you were to get rid of p-hat, okay, there's a hypothesized and there's our man-made, right? If it were one sample, if it were just one, what we were looking at, one like what you know already, this would be gone, this would be gone, and this thing right here, all we have is going to be, well, we have nothing with 2 in it. Okay, this is the test statistic for one variable, one sample. If we go back, you'll see it's P1, right? Hat, the difference from what we think it is. What we believe God's truth to be, it is P hat minus P1. Divided by the deviation, which is the square root of P1 Q1 over N1. But now, because we have 2, we have to bring that into account. And here we have our test statistic. Now, remember that if you actually did the distribution of the differences, it would look like this. So that we have this, now we have a test statistic Z hitting somewhere, right? That's a Z test, right? Okay, somebody tell me, what is the area from here on back called? Yeah, it's the p-value. There's a relationship there. Okay, now, if they tell you I want a confidence interval, and I want it with like a 95% degree of confidence, that means what you have left for alpha, it's 1 minus the confidence interval, is going to be equal to 0.05. Okay, now, if I'm doing I'm doing this as actually a two-tailed, do you see that? So now what I would do here is I would say whatever that is, I'm putting some theoretical, I'm just putting down numbers, but let's suppose right here. Okay, now what I've done is I'm saying, okay, now I'm going to call this area in red 0.025 because it's a two-tail. And I'll put this here at 0.025. 0.025, you see? So these, right, are going to be my critical values. Do you see they're different than the z-test? These are my z critical values. that I calculated by looking in the guts of the table to get another z-value for a critical z-value. If you want, you could put a z critical value. Different than the z-test. This area right here is all, if the test statistic hits here, what do? You fail to reject a null. You didn't say you proved it, you just said you failed to reject a null. That what? That there's no difference between the two. You understand? Okay, good. So here I'm trying to show you again the difference between p-value. Now, if the p-value, the area from here on back, is bigger than this on back, you can see you're in the accept area. Okay, and these will be the reject tails. Reject. Also here. Okay? But now this is a beautiful way of comparing a before and after situation, and this is your z-test statistic. I'm saying that before we had two poles, our z-test statistic, if we're using the normal, would have been p hat minus p, or if you want to call it 1, because it's all the same, and it'd be the square root of, then we would have the p hat 1 q hat 1 divided by n1. That would be the test statistic for one sample. This is what you're used to now. You should be. This is like practical in the sense that you'd want to see a before and after with the same group. Biostatistics in medicine, does the medicine have an effect positively or not? Right? That is a before and after, isn't it? And then you want to, eliminate the placebo effect. Okay. Let's see. Does people know what carpal tunnel is? Is your wrist sore? So, this is Statcrunch. So, we're going to compare two. So, this is the compressed nerve in the wrist. When you use the mouse a lot and you have this hand sitting there or whatever, it gets sore. It says, okay, a randomized control, 73 patients were treated with surgery, right? And 67 were found to have successful treatments. Okay, then you have 83 were treated with splints. You know a splint? It's like to hold the bone in place or whatever. And it was found that 60 were found to have successful treatment. Okay, so this is an actual data. It says this is from splinting versus surgery treatment, carpal tunnel, and these are the guys that were in the American Medical Association. Okay, and this is what they came up. Okay, so we want to know: is it surgery worth it, or is it better to get a splint? Is there a statistically a significantly higher success rate using an operation? I got this thing, they call it, what do they call it? Fisher's planters or plantar fissure or something. They get when your bone on your heel will keep growing, and it starts to puncture the skin on the foot as it gets like fingernail. Imagine it getting too long, but it's your heel bone. And it starts especially if you get older, it starts to feel like you're getting stepped on a thumbtack. And it's not very pleasant. It's almost like a hemorrhoid of the foot, so to speak. And I went to the doctor, the podiatrist, foot doctor, and they suggested surgery, right? And I said, well, okay, if you suggest it. But then I went to see another doctor, and they go, no, we don't do any surgery. We do stretching. So they give you these stretch things to do like this, like do on your tippy toes so many times a day. And it went away. I didn't do the operation, so. But anyway. Okay, so let's look at the stats. Okay, here's the difference between the two. 0.1949, right? And these are Z observed values, 3.12, and then the critical value. Remember the critical? That's the test where we're testing whether it falls. And then we have the P. Look at this P value. Can you see that's a pretty low number? Do you remember on when we had alpha divided by 2, it was 0.025? Can you see that is a lot bigger than the p-value? So you know we're going to be rejecting, or we're going to reject the null hypothesis, you see? Because when I do my graph, right, I'm saying that this p-value is so small, it's 0.0009, so it's just teeny little bit left. Clearly, and we were wanting a confidence interval of 0.025, right? Well, in this case, 0.025 is bigger than this area. This area would be your p-value, the red, right? And that p-value was 0.0009, and no, sorry, that was the yeah, that is a p-value, right? This guy. I should go here. Let me get rid of this. And this guy was my critical value, or what we call our alpha divided by 2. Okay? So I can tell by looking at the p-value, and I can tell by the confidence interval how much we want in the tail, whether or not we're accepting or rejecting the null hypothesis. No. We're either rejecting or we're failing to reject. Okay. Any questions? Okay, so let's try one. Okay, so now we're going to test the claim, testing claims about proportion, 2 different proportions. So we have to identify the null hypothesis. I think a lot of you that are doing your project, you should start with what is your null and what is your alternative. I mean, you can look for data too. Yeah, so you have, so the test statistic works along with the critical value, right? So your critical value, if your test statistics hit between here and here, you're accepting. The p-value is a little bit different, but we compare that with the alpha over 2. Okay, and it says p-values. Then state the conclusion about the null hypothesis. So this is called license plates. So what happens is that you have some states that people are driving around with one plate on the back of the car instead of one in the front and one in the back. So this is comparing which state has, is there a statistical difference between the proportion of people who are driving with only one plate in one state versus who are driving with one plate in another state. Can you see how that might be useful as far as, yeah? So they're telling you what you want your significance level to be. So that would be half of that on both 2 tails, yes? Okay, so then we have, so we had, it says among 2,049 Connecticut passengers, 239 only had a rear plate. And over in Connecticut, well, see, no, in Connecticut, among Connecticut trucks, 45 had rear. Based on the sample, a reasonable hypothesis is that the passenger car owner violates state law at a higher rate than owners. Okay, this is the difference between commercial trucks and cars in the same state. They want to know, this is a bigger number, right, than this, right? So when you look at it, you would say, yeah, I mean, these guys are getting away with it a lot more than the private driver. You would say that. But you can't say it that because you have to take into account the deviation of the data. It's not enough just to look at one. It's like, and I told you earlier, and you calculate the example of taking the mean of the number of the average deposits in a bank, all right? And then the manager or whatever asks you, are we doing better or worse? Well, our average is up. Our average is, went from $500 per to $1,000. So I think we're doing better. But no, you have to take into account the variance of the data. What happens if you have one dude that just deposited $1 million? One dude. That's going to upset the average for everybody, right? So the way you counter that is that your test statistic and everything else has to include deviation along with the number. That's why you can't just call it right here. The level of significance along with the deviation and along with the p proportion is what finally decides whether you accept or reject. you can't just say based on the average. You have to say, no, I have to look at my standard deviation. So it didn't work, this one. It says, this was the one that did for another program. It says, this was fast food, right? So out of 264, we got 54 that were not accurate. I don't know if you know this, but they make mistakes through the drive-thru. I hate that, don't you? He says, I didn't order this, or they forgot this. So, and then, okay, it says for McDonald's. So this was Burger King, and this is McDonald's. See, we have two proportions to compare. And so we're going to test the hypothesis, and then test the claim by constructing an appropriate confidence interval. So now, they want you to address this one by what, p-value? No. They want you to construct a confidence interval, and then you can see whether or not the test statistic falls in that confidence interval. No, okay. There's another one. Here's a bunch of examples that you could, so this is about stopping smoking. 198 smokers who underwent this care, and 51 of them no longer smoking after 6 months. And then they had another one, 99 smokers who underwent standard care program, and 30 no longer. So somebody could say, oh, 30 and 51, this must be better. You can't tell, because you have to know the variance of what's occurring in this other sample. We're no longer smoking. Okay. So this was another study. Actually, any one of you could go to one of these studies and see if you could reproduce it. It's already here. You know, you can go to this point, Journal of and see if you can find that, and then I'd like you to verify. In science, it's always important that you have peer reviews to go over the data to see if they operated correctly. So I see that as completely valid if you want to use this as a basis. All right, now, I don't know if you dream in black and white or in color. I don't even know if you dream in sound, if you hear sound, unless you're schizophrenic, I don't know. So here's another one, testing the claim about black and white, the people who dream in black and white. I don't know if I dream in black and white or color, come to think of it. But how many people know if the red lights is on a traffic light, is it in the top or the bottom of the light? Top? You think it's top? Yeah. Well, good. Somebody looked. Yeah, I mean, sometimes things are overlooked, so obvious that I haven't thought about it, you know. That's one of them. Do I dream in black and white? I don't know. Let me think. Anyhow, clinical trials of oxycodone. I think you know that can be used as a treat pain. So 52 developed nausea, and 175 didn't. And now they did the placebo. Interesting. The sugar pill. Right? And even there, 40 people didn't get sick, didn't get nausea. And they were given the sugar pill. Yes or no? Well, that's a great, test to do. To see, what if the proportions are not different, that tells you that this is not really that effective. It has the same impact as the sugar pill. Right? Now, this is not necessarily right. You have two groups. You have the one group that's in that's been given a placebo, and you know the group that's been in actual medicine, right? This is not paired data, because we're not looking from the one guy to the other guy. We're looking at two different samples, not necessarily before and after. We're doing before and after only to the extent that we're looking at how many of them were not nauseous. This should be all sorts of nice, good examples. Airbags. Here's that study right here. I don't mind. A random sample of front desk occupants involved in crashes. Out of 2,823, 31 of them were killed not wearing seatbelt. And then this one says, who wants airbags? And then, out of 7,000 occupied wearing seatbelts, 16 were killed. So we want to do the claim, it says, the claim that seatbelts are effective in reducing fatalities. This is all beautiful stuff, in my opinion. I mean, to be able to show evidence supporting these kind of things, this is powerful. Cardiac arrest, day or nighttime. When do you think the most heart attacks happen? Actually in the morning. And on Monday morning when you have to go to work. You die before you go to work. That's the ultimate excuse. I can't go to work, I'm dead. Okay, so the survival rates in hospitals who suffered cardiac arrest, out of 58,593 who had a cardiac arrest, 11,600 of them survived. Well, that doesn't look so good, does it? Out of 58,000? Maybe I just not eat as much. 11,604 survived? I don't know. What's that? 50? That's less than. What is that? That's like 20% survived. 20% of this. 20% of 60. That'd be about 12,000. You see what I'm saying? Okay. So among 28,000 who suffer from cardiac arrest, right, and then 4,000 of them survived and were discharged. Okay, so what do we want to say? We want at this significance level, right? So what does that make our alpha? Well, that is at 0.02, right? 0.01. So if it's two-tailed, we have to divide that by 1, right? And they want to test the claim that the survival rates are the same for day and night. So let's see. So what happened here? This was for hospitals that suffered cardiovascular assistance, arrested and survived or discharged among who survived cardiac. I don't know. It doesn't say which one's night and which one's day, does it? Well, anyway, one's night, one's day, and then we want to see if there's a difference. I think it's, you know, of all the math classes you take and taken, this one is like got to be one of the most applicable one that you can use right away, and it has substantial impact on decision making. Okay, I think you've heard of this echinacea. I don't know how to pronounce it. Echinacea. The rhinovirus. There are many of them. Viruses that are the cause of the common cold. In England, they have a place where you can get a job, and your job is catching a cold. And so you go in there, and they put some droppers in your nostril, and they drop the virus right into your nostril. And then the way they measure the severity of the sickness is that they weigh the amount of snot rags. So they know what a tissue weighs. So they put it on there, and then the amount of snot coming out of you is a measure of how bad the cold is. And so you get paid for that to have a cold. That's not a bad job, I think. I don't know. Not sure I'd like it, though. But I wonder if they build up kind of resistance. Cell phone and handedness. You get that. This one here, denominating effect. A trial was conducted with 75 women in China, given 100 yuan. Juan. If you don't know how to do it, you have to call Juan. Juan bill, while another 75 women were given 100 yuan to form in the form of smaller bills. So they were given a 50, right, and plus 20 plus a 5 yuan bill. You should get used to this word because we'll be using one here pretty soon. The dollar will be replaced. That says the denominator effect. There's the Journal of Consumer Research. Tells you the volume, 36. Look it up. We want to use this, and given a smaller proportion of women in China spend some money when compared to the proportion of women given the same amount in smaller bills. Interesting question. I mean, it's like they find when they're pricing, when you go to a fast food restaurant or almost any place where you serve yourself your own soft drink, right? They give the soft drink, and they find if they price, if they price it like the large too much higher than a medium, then people don't buy large, right? But if they leave a large price at the high price what it was, where people weren't buying, and they increase the price of a medium size, they start buying the large because they perceive the difference between the two is not that much. And it's a lot of psychology involved. As a matter of fact, I've seen people, pay for a large cup, and it's all you can drink. So why would you buy a large cup? Anyway, it's all psychology. So anyway, I hope to see that, listen, with this much, you can see that there shouldn't be no end to the possibilities of what you can do for a study. This thing, I don't know if you know this, but you can, people who have heart disease or think they have heart disease are taking a slow dose of aspirin. What does aspirin do? Does anybody know? It thins the blood, so less clotting, so less heart attacks, they're saying. So they're taking this really low 20 milligram aspirin every day. And that's stopping the platelets from collecting on the arteries because it's not clogging as easily. Of course, too much of that and you'll bleed out, right? Too much aspirin. It's just okay, so that's what they did here, and this is also in the New England Journal of Medicine. So all of these would be really nice. How about lefties? Versus use your left hand versus right. Okay, I wanted to actually get on. Oh, here you go. Here's some air stuff you might like. This is for airports. Ground versus helicopter for serious injuries. Well, what do you think? A study investigated rates of fatalities among patients with severe traumatic injuries. Out of 61,900 patients transported by helicopter, 7,800 died. Among 161 patients transported, 17,000 died. Now, this was with ground service. Would you expect that, that it's better to have helicopter service than being driven by ground? I mean, when they get shanked over at the prison, right? What do? They fly them over to Reno, don't they? Well, wouldn't you expect that to be faster than if they drove them over? I would think helicopter's faster than driving. I would think by a long shot. And not only that, well, it's expensive though. They're saying it's around $30,000 a trip. Or every shank, where they're bleeding out. I was at the high desert first semester there, and I had, while lecturing, on 3 different occasions, I had the helicopter come in right into the prison to load up these guys. And the third guy, I was like teaching, and I see the helicopter come in, and then I'm teaching, and then I'm thinking in the back of my mind, when are they going to leave? This dude's bleeding. I go, why don't they leave? And I found out later that the helicopter was near capacity, weight capacity. And they couldn't find a guard that's skinny enough to be put in the helicopter to go to Reno because they weighed too much. So they're scrambling for a little shrimpy guard or female guard. And finally they found one and the helicopter took off. Well, that might be an argument why it's better to go by car. Because they can't find a thin enough guard. I don't know. So, here it is. Journal of American Medical. Okay, here we go. Okay, now, finally. This equation here, to use it if you're going to be doing your own sample. This tells you what kind of sample size you should be looking at according to the error term and the alpha over 2. Okay, you probably won't use that because you'll be doing now. This is called, I don't think any of you use this. This is the exact test. So it's a test that you can use another way of calculating a p-value, but I don't want to get into it. It's not worth it. I mean, Okay, here again, just to make sure that the equivalence of the hypothesis test compared to the confidence interval. Two different simple random samples are drawn from two different populations. The first sample consists of 20 people and 10 have a common attribute. The second sample is 2,000 people and with 1404 of them having the same. Okay, compare the results. There it is. Your null. P1 proportions are the same. That's your null. That's the same as saying P1 minus P2 equals 0. And then we have the significance level. Yeah? So if it's a two-tailed test, then you'll take that divided by 2, right? And then you have the confidence interval. That's how you would construct it. So let's construct one. Okay. So what do you need to look for? Just like with one thing, sometimes you have sigma and sometimes you don't. When you don't have it, you use S, right? So this is a case, and you usually don't have it, so I don't know why they keep including it like this, but they have one section one with and when it's unknown. Okay, and here, look, they're not assumed to be equal. I'm talking about deviation, right? Okay. Okay, so here's how you want to work that. The samples are independent. That means that whatever's happening here is not affecting what's happening over here, right? You had one group that you test out and there's a certain proportion, and you have another group. Does the outcome of this experiment affect this other one? If it doesn't, then they're independent. Okay? So you want two samples that are independent. Sample values from one population that are not related or somehow naturally paired matched, because we have a different test statistic for paired data. Okay? So for this particular test of testing proportions, you want to consider whether you're talking about a paired data or not. Everything that I showed you from now on, I think, was not paired. So two samples have different sample sizes with no missing data. They must be independent from each other. If the two samples have the same sample size, the samples may or may not be independent. I think it's assuming that if they're the same size, they're like paired. If they're the same size. Okay? Oh, here's one. It's a data set 1 body data in Appendix B. I think we have that. It says the following heights in centimeters of the sample of men and women. The two samples are not matched according to some inherent relationship. Okay? They're actually two independent samples that happen to be listed in a way that might cause us to incorrectly think they are matched. So these are two groups, independent groups, and these are the heights in centimeters. This one's pretty tall. 186. Actually, a bunch of short dudes. That's okay. They're still worth them. Okay, and then now we have dependent sample. Okay. Now we have the height of the husband and their wives. I'm not sure why that's dependent. I don't know. 5 of these pair heights are listed below. These two are dependent because the height of each husband, is matched with the height of each wife. So it's husband, wife, husband, wife, husband, wife, husband, wife. Guess what? That's a difference. Guess what? That difference has a distribution. That distribution can be tested. Let's see if we can use, okay. All right, so here we go, finally. Now, okay. So, hypothesis test, of course. Construct a hypothesis test claim about two independent. This is independent. And then construct a confidence interval, estimating the difference between the two population means. So, mu is the population mean. We all know that, I hope. Sigma is the population deviation. N1 is the size of the first sample. Now, notice we're not talking about population. We're talking about the size. Remember, that's capital N for these guys. This is a little n. So x bar is the sample mean, which we use as the best predictor for mu, yes? Do you remember the arrow going this direction? And here we have S, sample standard deviation. Yeah? Is the best for this, right? Okay. So let's try it. Oh, okay. Now, here are some of the requirements, right? We want, remember the n sample sizes. If we're going to use a normal distribution as opposed to the binomial, if n and n2, n1 are greater than 30, right? You guys are not texting each other, are you? You could just write little notes and then hand it back and forth. They're both like, I can tell you're on the same team. Okay, now, we're going to test two means. We're not proportion right now, are we? Two means. Look at what this one is. That's man-made minus man-made. That's the difference between the man-made averages from two samples. This is a different sample average, sample 1 and sample 2. Yes? And this is the theoretical mean, the God. And we want to know if there's a difference between the differences. Is there a difference between the hypothesized averages and that's coming from our sample? Now, what is all this business about? This business is about, because now it's a little bit more complicated. It has this extra term, which is still, it's the s squared over this, it's the variance of the second group divided by its sample size, right? And this is the equation. Okay, now, depending on the distribution that they use here, I think now notice that this is a t, so they're using a t, student t distribution. Okay, and then degrees of freedom. You have degrees of freedom with the t distribution. So we have to calculate the degrees of freedom. Use the following for determining the number of degrees of freedom. Result in different numbers, so. Okay, so A plus B, that's this thing here. Remember, that was the one that's right here. You see it? S1 squared N1. And then you have B, and that's going to be that. So they replaced these guys. Okay, so this is degrees of freedom, df. So they're saying that this plus this, that amount squared, plus divided that will give you the degree of freedom. Would you remember what the degree of freedom was with one sample? Just n minus 1. But here we have a little bit n minus 1 here and n minus 1 there. But because they're combined, it's different. It's not so easy. I don't know. And you do your final. You know, you can have the book there to look at the formulas. So you don't necessarily have to memorize them. But clearly, you're going to know how to use what test statistic for what thing. Okay. Here's table A3 for the t distribution. Let's go over here. Okay, now the confidence interval. Okay, I can remember this. I can remember when we were just talking about x bar 1 minus the error term binding mu 1 by x bar again 1 plus error term. If you remember, we were putting this in bracket and giving a probability of some kind of confidence interval. Look at the difference. What's the difference? Well, we got two averages. We have the one and the other, minus the error term. Do you see it? Then we have what we hypothesize, that there's no difference between the two. All right, there's a true mu in the single case. There's a double case. And then error term. You see the similarity? It's quite similar. And now, what is that error term? That is the sum of the two deviations square rooted, and there's your t sub alpha 2. Remember when you take alpha divided by 2? Well, you're going to do that, but now we're going to do it with a t distribution. It looks a lot like the normal. But this right here is the alpha divided by 2. And alpha divided by 2. And what is this tested? What is this critical value? This critical value of fact right here is this value, T sub. It's whatever, you calculate the area, you calculate what your Z value or your T value is. That's a critical value here, a T critical value here, and a T critical value here. Okay? So that critical value enters in through here where there's a T. Can't see it, but there's a T. There. T sub alpha over 2. Okay? As we go through, you'll see it's pretty much equivalent to the single case, except, you have to take into account. Now, you can also test using p-value, right, instead of using a confidence interval. Correct? All right. So now we have male professors and female professors rated differently by students. That's interesting. I wonder how I'm rated by students, by woman versus man. So this is the rating for females of a professor, and this is the rating of males. I'm not sure if it's a scale out of 1 to 5 or what. Oh, but here's a data set's already included. That's another thing. Some of these have a data set ready to be loaded into Crunch. Does it appear to be a difference evaluation score taught by female professor or male professor? So this is what a female professor received as scoring, and this is the male. So we're going to have to start to figure out what? The deviation of this guy, the deviation of that guy, the average of this guy, the average of that guy. Yeah? And we want to see if there's a statistical difference. What's the requirement? What's one of the requirements? Well, remember there had to be 30 of them and something like that. Now, it says now, the values of 2 population standard deviations are not known, okay? So that means sigma is not known. But we can still calculate the S. Yes? Okay, and are they independent? I think they're independent, unless they're married or something. The sample are simple random, yeah. Oh, here the sample is fewer than 30, obviously, yes. So we need to determine whether both come from a population having a normal distribution. And you can do the quartile plot, the QQ thing on the thing to see if it's a normal distribution. So the requirement is all those are satisfied. Here we finally get into our null hypothesis. Okay, so here's the claim that the 2 samples, the average, God's truth between a male and a female professor, that there's no difference in their average score. All right? The alternative is that there appears to be a difference. Why? I don't know if you can make a statement, about female versus male professors. If it could be just the personality of these 2 people, I don't know. So there's the null and there's the alternative. Okay, so this is actually working one through. And that's the data already there. So, okay, now, it looks to be getting like complicated, but it's just tedious. So here is the significance level. They're telling us what the significance level is. That would represent a confidence interval of like 0.95. But this is alpha. So because the 2 are independent, we are testing a claim about 2 population means. And we use the T distribution. All right, because where n was less than 30. Okay, now let's calculate our test statistic. Look at this monstrosity. But it really doesn't bother me because I can see it's much like a single statistical test where it's just x bar and mu. We're comparing the difference here, but here we're comparing the difference of the sample means versus the hypothesized means, divided by their sum of their individual deviations. Are we okay? Okay. Now, in order to find the p-value, we have a test statistics of 0.660, right? So 0.660 is what? Is minus 0.60, yes? So how does that look? It looks like this. And where's the test statistic hitting? Well, this is 0. Let's say it's hitting at, well, so where is, how far back is this? This is like You know, this is like, let's say that the t-statistic's hitting about right here, 0.660, something like about right here. So we have to see if that's within our accepting range. Okay, so that's our test statistic. You take the sample, subtract it, you take this theorized hypothesis, mu1, mu2. We're saying we think it's equal to 0. Right? And now we're going to see where that hits. Okay. Now, the degrees of freedom. The number of degrees of freedom is the smaller of n1 and n2. So this is a little different. We didn't have to calculate that degrees of freedom. This is easy. So we just picked the smallest and we subtracted 1, which is 11. Because one of them has 12 units and one has 15. I'm trying to work one that we can use Statcrunch. So we say the p-value is greater than the significant level. Remember, that was 0.05. And the p-value is right here, 0.51. Can you see this is substantially bigger than this? Meaning that this isn't, the test statistic is falling into the fail to reject a null hypothesis. Okay? All right. Okay, the critical value method, that's easy. That's finding the z values wherever alpha divided by 2 is. Whatever area that covers and you want to find the z or the t values, you have to look in the guts of the table, or it will produce, or you go to the stat thing. So, so it says this is a relative easy way to avoid the messy calculation